Thank you, Sabrina. So first, I would like to thank the organizer of the program for setting up this very nice event and for giving me the opportunity to talk. It's always a pleasure to be back in Vienna. So in this talk, I will discuss Carrollian amplitudes, celestial symmetries, and Twistor space. And this will be essentially based on this work that was done recently in collaboration with Lionel Mason and Akshay Ileshpur-Srikan in Oxford. So the question that I would like to ask in this talk is how to formulate flat space holography. And by that, I mean a correspondence between gravity in asymptotically flat spacetime. And for the purpose of the talk, I will essentially focus on the four-dimensional case and a lower dimensional field theory without gravity. So here I will essentially take a bottom-up approach, which means that I will try to deduce some aspects of some putative dual theory, starting from what we know of gravity in the bulk. And in this context, there are two proposals that have been discussed in the literature. The first one is, of course, called celestial holography. And in that case, the dual theory is a two-dimensional CFT, which is living on the celestial sphere at infinity. But there is another proposal which has been discussed more or less in the same years, and which is called Carrollian holography. And in that case, the putative dual theory to 4D flat space is a three-dimensional Carrollian CFT living at null infinity, so at scry plus and scry minus, which are future and past null infinity. I will define more precisely what I mean by Carrollian CFT in the talk. But let me just say here that even if these two proposals look completely different a priori, even just by the dimensions of the dual theory, you can actually show that they are related. Okay? So it means that in principle, you are free to choose either of these two approaches to study flat space holography. And in this talk, since it's a Carrollian workshop, I will focus on this Carrollian approach to flat space holography. So let me state a bit more precisely what's happening. So Carrollian holography suggests that gravity in d+1 dimensions in flat space is dual to d-dimensional field theory that is living at null infinity. And here we start with a very basic statement about holography, which says that the asymptotic symmetries of the bulk theory correspond to the global symmetries in the dual theory. And we know in particular that the asymptotic symmetries in flat space are given by these BMS symmetries. And in a very nice work by Duval, Gibbons, Horvath, it has been shown that the BMS symmetries in d+1 dimension, so d+1 is the dimension of the bulk, they are isomorphic to the conformal Carrollian algebra in d dimensions, which is defined intrinsically at the boundary. And so just by this observation, if you want a theory that is living at scry, this should be a Carrollian CFT. And by that, I mean a theory that exhibits some conformal Carroll or BMS space-time symmetries. So let me also say that these kind of theories can be constructed very explicitly by just taking the c going to zero limit of standard relativistic CFT. So c is the speed of light here, and this is called the Carrollian limit. So we have explicit examples of such Carrollian CFT. Let me also say that this Carrollian holography proposal follows a similar pattern than the ADS CFT correspondence because it's a codimension 1 holography. And in particular, most of the results that have been obtained in this approach are found by taking the flat limit of what we know in ADS CFT. And this flat limit in the bulk, which amounts to taking this ADS radius to infinity, implies this Carrollian limit that I was mentioning before at the boundary. And so this explains in practice on how you can start from a CFT living at the boundary of ADS and obtain a Carrollian CFT in the flat limit living at the boundary of flat space. Sure. Mm-hmm. Yes, so they are studying the null string. Basically, they are taking the Carrollian limit on the worldsheet. That's the first reference I saw explicitly this kind of limit. So let me here flash a few results that have been obtained in the Carrollian approach. And it was particularly successful in the context of 3D gravity, where the flat limit works very well. So let me mention a few results. For example, if you start with the gravitational solution space in asymptotically ADS3 spacetime, and that you take the flat limit, you get the asymptotically flat solutions in 3 dimensions. And you can show that this limit works very well at the level of the symmetries, where you can start with the conformal symmetries in 2 dimensions and recover the BMS3 symmetries in flat space. You can also match the entropy between flat space cosmologies and Carrollian CFT theory at the boundary using some Cardi-like formula. You also have some formula for the entanglement entropy for this putative Carrollian CFT. You can compute some correlation of a Carrollian stress tensor at the boundary using some kind of holographic renormalization procedure. You can build some effective action for the Carrollian CFT at Scry. And in an interesting paper, I think we show that there is an analog of the holographic anomaly, but for flat space. And this is basically obtained by taking the flat limit of what we know about the anomaly in ADS3 CFT2 in a very careful way. Let me also say that some of the results can be uplifted to the 4-dimensional case. And in particular, Sabrina gave a very nice talk about that to review these aspects. So let me just say that if you take the flat limit of the gravitational phase space in 4 dimensions, you can obtain the solution space in asymptotically flat spacetime, and this also works at the level of the symmetries. There is a subtle story with the radiation. The flat limit works also very well at the level of the free gravity correspondence. So if you start with the free gravity correspondence in ADS and that you take the flat limit, you find that there is a Carrollian fluid living at Scry. You can also write some Carrollian CFT actions at the boundary that capture some aspect about gravity in 4 dimensions. But there was an important piece missing in that story, and this was the relation with the 4-dimensional S matrix and the celestial amplitudes. And Stefan already gave a very nice talk about that last week. So what I will do in this talk is to try to define a notion of Carrollian amplitude, and I will give some properties of these objects. And the goal here will be to encode the bulk S matrix into some boundary Carrollian CFT correlators. So that will be the main objective of this talk. Okay, so let me start with the setup that I will be using. So here I will work in the so-called planar boundary coordinates, which are given by these U, R, Z, and Z bar coordinates. So Z and Z bar are just the coordinates on the celestial sphere, and U is this null time along Scry. So these coordinates are related to the Cartesian coordinates in the following way. So that's the change of coordinates. And in particular, you can show that the Minkowski metric in these coordinates will take the following form. So for the experts, this is not exactly what people call the boundary coordinates, because usually you have a minus du square and you have the round sphere metric here. But these coordinates are kind of simpler because you get a flat metric here for the transverse metric. Notice also that the radial coordinates takes value in R, so they take a value from -infinity to +infinity. And in particular, Scry plus and Scry minus are both described by these set of coordinates. So if you take R to +infinity, you end up at Scry plus. But if you take R going to -infinity, you will end up at Scry minus. Now, if you take the limit R going to infinity, starting from this metric in the bulk, you get this Carrollian structure, which is induced at the boundary. So it will be given by this degenerate metric here, living at Scry. And you see that there is a 0 in front of the du square. And there is this vector field here, which is in the kernel of the metric. So that's what people call a Carrollian structure. Notice that there is a kind of natural identification between Scry minus and Scry plus in these coordinates. So if you start with a point at Scry minus with u, z, and z bar coordinates, and that you follow a null geodesic in the bulk, you will end up with a point with the same coordinate, u, z, and z bar, but at Scri+. So it will be important for us because it means that I can discuss everything that is happening at Scri+, providing I keep track of what is incoming or outgoing somewhere. So now the BMS symmetries can be seen as the conformal symmetries for this Carrollian structure induced at infinity. And you can show that they take the following form. So this is a vector field at the boundary of flat space. And this is parameterized by two types of functions. So you have the T function here, which are called the supertranslation parameter. So they depend on Z and Z bar. And you have the Y and Y bar function here, which are called the superrotation parameters. And they satisfy the conformal Killing equation in 2 dimensions. So now the question that I would like to ask in the talk is, can we encode the bulk S matrix into some boundary Carrollian CFT correlators? And here the strategy will be to start from the bulk field, push it at the boundary, so that you can get the boundary value of the field. And basically, I will identify the Carrollian operators in my putative dual theory with the boundary values of these fields. So let me do that explicitly. I will start with a spin S field in the bulk, which is massless. And S here can be 0, 1, or 2. So it's not necessarily a graviton. And I can expand this field in a plane wave in the following way. So A and A dagger are just the usual creation and annihilation operators. So there are several notations here. This I is just a multi-index notation that will depend on the spin of the field that I'm considering. P mu is just a momentum. And since I'm considering some massless field, this will be a null momentum. So it will be parameterized by the energy, omega, which is positive. And Q mu, which basically labels the direction of the momentum. And this is parameterized by W bar, the coordinates on the celestial sphere. So epsilon here is just the polarization tensor of the field. And now what you can do is to take basically R to infinity to reach the boundary. And you can use the so-called stationary phase approximation to get some explicit expressions for the boundary value of the bulk field. So if you take R going to plus infinity, you will end up at Scri+. And the phi out here, which is the boundary value at Scri+, will be expressed in the following way in terms of the creation and annihilation operators. And similarly for the field at Scri minus, so you just take R going to minus infinity instead. And these boundary values of the bulk field are important because they correspond to the insertion operator for a massless scattering between Scri minus and Scri+. So now I would like to define a notion of Carrollian field intrinsically at the boundary. And to do that, I will take a definition which is analog of a conformal field in a CFT. And this is what I will call a conformal Carrollian primary. So this is a field that depends on u, z, and z bar. It's living at Scri. And I will define it as a field that transforms in the following way under the action of the BMS or the conformal Carrollian symmetries. So here you recognize T, Y, and Y bar, which are the BMS parameters. And there are also some weights that appear in this transformation, so the K and K bar here, which are called the Carrollian weights. And these are, if you want, the analog of the conformal weights in a standard CFT. So let me mention that these Carrollian primaries actually transform in unitary representation of the Carrollian symmetry. So this has been shown in these papers, which means that these are the kind of representation that we want to consider for holographic dictionary. Yes, yes, the induced representation. Yeah. Yes, yes, yes. Mm-hmm. That's the point of this paper, actually. So now the kind of object I would like to consider in the following are correlators of these Carrollian primary operators. So these will be objects of this form, and these will be correlators living at scry. And let me mention a technical point that will be useful for us in the following. So if you start with a Carrollian primary, and that you take a time derivative of it, so derivative respect to du, you get a Carrollian descendant, but you can also show that it's a Carrollian primary, which will transform exactly in the same way, except that the weights will be shifted by 1/2 and 1/2. Okay, so now I can state my correspondence between my bulk and boundary objects. So the first thing to do is to identify these Carrollian primary operators that I've just defined at the boundary with the boundary value of the bulk field that were obtained by taking the larger limit. Okay? So that's the first identification I'm doing. And by doing this, you can show that the weights here, k and k bar, that are appearing in the transformation law, will be completely fixed in terms of the helicity of the bulk field. So the helicity is given by J. And you see that there is also this epsilon that appears in the Carrollian weights, k and k bar, which will be +1 or -1 depending on if the operator is inserted at scry plus or scry minus. So if it's outgoing or incoming. So for instance, if you take the case of gravity, in that case, the spin is equal to 2, and the Carrollian operator will just correspond to what we call the asymptotic shear. Okay? And you can check that these Carrollian weights are consistent with the transformation of the metric under diffeomorphism. Right, so here there are two options. Either you keep the two copies of scry, so scry minus and scry plus, and then you glue them together in a non-antipodal way. That's the first way to do it. But here, since I'm using this nice coordinate system, I can work with only one copy of scry and forget about the other, except that I keep track if the operator is inserted as scry plus or scry minus with this epsilon. So this epsilon is fundamental to say if the particle is incoming or outgoing. But I can only use these u, z, and z bar coordinates without referring to scry minus. Right, so we use this antipodal matching when looking at the BMS flux balance laws, and that we were trying to relate them from the Carrollian to the celestial picture with the soft theorems. And it was important to have this antipodal matching because you wanted to identify the Carrollian stress tensor at scry minus plus with its value at scry plus minus. And it was important that there was a cancellation. So I would say it's by construction of the Carrollian manifold on which you are considering the theory. So if you are considering this theory on the two copies of scry, and that you glue these two copies antipodally, then geometrically the antipodal matching is identified. So we put it in some sense by hand, by construction of the dual theory. Yeah. I cannot give a proof of the antipodal matching in the, so it's by construction. It's a kind of input that we give to for the construction of this theory, but I don't have a proof of that. I would say. So maybe I can show this diagram. So the nice thing about these coordinates is that basically each point at scry minus, at least in Minkowski space, is identified with a point at scry plus. So you have a kind of antipodal identification because you are starting here with a point on the celestial sphere, and then you get an antipodal point on the celestial sphere, but at scry plus. So that's maybe how the antipodal matching is implemented in practice, just geometrically by following the light rays. Yes. So these are the two possible ways to do. Either you work only with one copy of scry, but then you have to keep track of if the operator is incoming or outgoing, so epsilon is +1 or -1, or you work with the two copies of the cylinders, and then by construction you glue them antipodally, and there is nothing to. Yeah. Mm-hmm. Right. So sorry, if I start here with a point, so the light cone will not cover all scry, right? Yeah. Yeah. Yeah, so if I take this point, for example, and that I consider is light cone, I guess the light cone will intersect scry in the following way. Yeah, so it will not cover this part of scry plus. So this fall guy, you mean, or yeah. Yeah. Ah, right. Okay. Yes. I agree. Yes. Right. Oh, okay. So maybe let me make a comment about that. So once you are considering these two copies of the cylinder and that you are gluing them together, there is a way to distinguish the gluing surface compared to all the other cuts of the cylinder, and it's because the Carrollian vector field that is defined here will vanish at this place. That's the way you can identify this gluing surface compared to the other cuts of scry. Right. So you have to keep track of that. That's an important piece of the geometry. So we chose the antipodal matching such that we can use all the arguments concerning the soft theorems. There was no geometric argument to do it. We choose to do it. It's a kind of ingredient in the construction.
Yes, but is that a smooth choice?
Yeah, it's.
Anti-antipodal, we will have a twist at some point.
Well, in principle, you have several ways to glue two cylinders together, and we decided to glue them antipodally, but I don't think we are forced to do that. I think it's an ingredient in the story. There is nothing forces us to do that. Okay, so that's how we define the Carrollian operators in the putative dual theory. And here, let me emphasize that we keep track of epsilon, so +1 or -1, depending on if you are at scry plus or scry minus. And then the next step is to define these Carrollian correlators at the boundary, which are correlators of these Carrollian primary. And they will be obtained from the usual scattering amplitudes, which are written here in momentum space. So they depend on the momenta, which are parameterized by the energy, and z and z bar, the coordinates on the celestial sphere. So this is the momentum. And basically what you can do is to perform a Fourier transform with respect to the energy. So with respect to the energy of omega. And at the end, you obtain an object which is living in position space at scry. Okay? So this depends only on the coordinates at scry plus. And I will identify this object in position space with correlators of Carrollian operators. So this is what I will call a Carrollian amplitude because of its interpretation in terms of correlators of Carrollian CFT operator, and this is by analogy with the celestial amplitudes. Let me also say that this dictionary has the nice feature that the extrapolate dictionary takes a very simple form. So if you start with a bulk correlator in position space, and that you take R going to +infinity or -infinity, you will end up with the correlators at the boundary, which correspond exactly to this definition of Carrollian amplitude that I gave before. So just by construction, we have these two kind of dictionary to build the Carrollian correlators. So now you can show that this identification that I'm doing between the Carrollian CFT correlators and these amplitudes written in position space at Scry is consistent with the Carrollian CFT ward identities. Okay, so these correlators will satisfy these ward identities for the weights that I was providing here. And so it's a bit like in a CFT where the low point correlation functions will be completely or partially fixed by the symmetries of the theory. So in particular, the 2-point and the 3-point functions will be fixed. But the higher point function will provide some non-trivial information about the dynamics of the theory. So that's why we want to compute such higher point function. But here, let me just solve the ward identity for the 2-point function. And if you do that in practice, you can show that there are two branches of solution. One is called the electric branch, and it's U-dependent, so it will involve this factor of U1 minus U2. And it will also involve this delta function with respect to the angles. Okay? So this reflects the ultra-local nature of the Carrollian CFT. But there is another branch, which is time-independent, and which corresponds to the correlation function of a CFT in 2 dimensions. So a CFT living in 1 dimension lower than my Carrollian CFT. So I will argue in the following that this electric branch is the one which is relevant for the scattering amplitudes in flat space. And you can already see that because of the presence of this delta function here, that if you want to encode some information about the momentum conserving delta function in the bulk. This comes from the symmetry, I would say. And you can show that in practice, these are the kind of objects that you get. Yeah. Yes, right. With this identification of the Carrollian fields, you can show that this will respect exactly these kind of constraints. But I don't have like a kind of intrinsic interpretation of that. Yes, that's right. Mm-hmm. Yeah, exactly. So this will be consistent with the bulk analysis, that for sure. But is there an intrinsic Carrollian interpretation of that? That comes from the symmetry, I would say. That's my best answer. Yeah, so let me mention one thing that I can kind of emphasize is that this electric branch involves this delta function, which is very natural from a Carrollian CFT point of view. And we can show indeed that 50% of the Carrollian CFT that has been built in the literature will involve this delta function in the 2-point function. And this is in contrast with the celestial holography approach, where you also get some delta function in the 2-point function, but which is very exotic from the point of view of a 2D CFT. So I think that it's a nice thing about the Carrollian holography approach. Right. So I would say for the moment, I cannot make a very clear statement about the interpretation of this possible second branch in the Carrollian CFT. I suspect that it could be related to some soft modes, because here I'm essentially in this talk considering some hard scattering. But we know that the soft modes obey some correlation function, which are time independent. So this might be capturing this. But I didn't do any concrete computation in that context. the delta functions? Mm-hmm, mm-hmm. You say how from the bulk perspective you can obtain something like this?
No, but
That's right. So exactly, if you take U derivative, you just eliminate the magnetic branch. Yes, that's true. Yes. At the end, you only end up with the, yeah, exactly. And actually, in the talk, I will really focus on this branch because I will take time derivative of the two-point function to avoid the divergences. Yeah. Ah, sorry.
No. The thing is that in Celestial, when you have the delta function, you perform, yes, thank you. you perform a shadow transform or CFT. The thing is that if you're thinking about ADS4 CFT, we have a shadow in the CFT. Three-dimensional. You have an idea how to define this shadow also for the Carrollian CFT in 3 dimensions?
No, I've never looked at it.
Do you think it will involve U as well, or just the Z and Z bar?
A good question. I've not looked at it. Maybe it's interesting. So I remember the talk of Simon yesterday, where he was saying that there was a way to go from an electric or a magnetic branch.
Yes.
And maybe this relates to that you can eliminate some kind of delta function, and the price to pay is to eliminate the U dependence, but I don't know in practice how it's working. Yeah, so I've not looked at that. That's the safe. Okay, so I mentioned before that you can take a time derivative of Carrollian primary. This will be important for us. For instance, you can, instead of considering for gravity correlation function of the shear, you can also consider correlation functions of objects which are genuine primary under the full BMS symmetry. And for example, these leading order in the peeling theorem. So these have some kind of advantages to consider these objects instead of the shear. But let me say that if you start with a Carrollian amplitude, as I defined it before, and that you take U derivative with respect to this, U derivative like M1 U1 derivative and Mn Un derivative, that you end up with these Carrollian amplitudes of descendants, but which can also be interpreted as primaries, okay, with shifted weights. So in particular, just taking one derivative will be interesting for us in the following. Yeah. Right. Yeah. That's. No. That's a big difference between a CFT and Carrollian CFT. That is completely legitimate to take the U descendants, and you can show that they are honest primary. And in particular, so that will allow me to relate that with the proposal of Carrollian correlators that was discussed by Arjun and collaborator in this paper. Yeah. Mm-hmm. Right. Yes. 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 That's right. Yes. 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 So I think this will have some implications for this modified Milling transform. So that's I want to comment on that. So just let me say that these du derivatives are useful if you want to kind of suppress some divergences that can appear in the correlator. So I will give examples of that later, but basically these Carrollian amplitudes might involve some IR divergences. And to get rid of them, you can just take some du divergence, du derivative. So now if I take the analytic continuation of M, which is the number of du derivatives that you are taking, you get this integral transform here. And this is called, in the literature, the modified Milling transform. And this has been used, for example, to regularize Milling transforms of graviton amplitudes. And I think that this kind of little construction clarifies the link between this alternative definition of Carrollian amplitudes, because we are just starting from what we call Carrollian amplitudes, and which are obtained by Fourier transform of the usual scattering amplitudes, which means that we are able to encode all the information about the S matrix. So there is nothing wrong about this formula. This has all the nice transformation properties under the action of the Carrollian symmetries. It's just that it's redundant, because it comes from some descendants. Okay? So now the link with celestial amplitudes. So the celestial amplitudes can be defined by taking the Milling transform of the usual scattering amplitudes here. So you get this celestial amplitude here that can be reinterpreted as a correlator of operators in a CFT, and the CFT is living on the celestial sphere. And basically, if you want to go from Carrollian amplitudes, which are objects in position space at scry, to celestial amplitudes, which are objects in Milling space, you have to take this combination of the Fourier and the Milling transform. Okay? So that allows you to match the Carrollian amplitudes with the celestial amplitudes. You also have a similar relation at the level of the operators. So here, in the right-hand side, you have a Carrollian operator that is living at scry. So it depends on the u, z, and z bar coordinates. And in the left-hand side, you have the celestial operators that depend only on z and z bar. And delta here is the conformal dimension. And j is the 2D spin from the point of view of the 2D CFT, which correspond to the helicity in the bulk. And basically, what this integral transform does for you is that it trades the time dependence of the Carrollian operator for this conformal dimension in the celestial CFT operator. And this is somehow how you can understand that you get a continuous spectrum for the 2D CFT. It's because you have to replace this continuous variable in the Carrollian case. So it's a kind of intuitive way to see it. Yes, exactly. Yes, yes, yes. We have 2 epsilon in the story. Yeah, yeah. It's the sign. Right, right. So let me say that this identification is compatible with all the works that have been done in the literature concerning the different bases of scattering amplitudes, and in particular, the extrapolate dictionary in Carrollian holography agrees with the extrapolate dictionary in celestial holography that was discussed by Sabrina and collaborators. Okay, so now let me give you some examples of Carrollian amplitudes. So I will start with the simplest example, which is the 2-point function, which is given here in momentum space. And what you can do is just to apply the receipt, so taking 2 Fourier transforms of this amplitude to get an object which is living purely in position space. So this is what I'm doing here, and the first Fourier transform can be done easily thanks to this delta function. But the problem here is that if you want to perform the second Fourier transform, you get this pole in 1 over omega, which means that the 2-point function here is IR divergent, and you have to introduce a regulator in the story to discuss this 2-point function. You can do it, and everything is consistent. But here, for the purpose of the talk, I will just use this statement that you can take derivative of Carrollian amplitudes. And I will take the derivative with respect to U1 and U2 to get this Carrollian amplitude here. And what you can show is that this is completely consistent with the Carrollian two-point function in the electric case that was the solution of the word identities. Okay. So in particular, I want to match here with Claudius' talk, where there was a similar two-point function that was appearing in the definition of the state. So everything is compatible with the symmetries and what we know from the scattering. Yes. So the k are fixed by the like this. So you have to take these relations into account. Yes, yes, yes. Yeah. I think we used two different regulators and we ended up on the same correlation function. So, but maybe this does not exhaust all the choices. That's the only comment I can make. The form of the two-point function, if you introduce this regulator by putting a cutoff here in the integral, is basically 1 over epsilon, where epsilon is very small. Then you get a log of U1 minus U2, and then you get a sine function of U1 minus U2. Multiplied by this delta function, but that's what I can say. Otherwise, you can just keep the integral representation and treat it formally, and check that it's consistent with the word identities and everything. Right. Okay. Okay. Potentially, yeah. Thanks. Yes, yes. So if you derive respect to U, maybe something that I didn't mention is that this regulator is U independent. You can show that if you put it explicitly, there will be no dependence in U, which means that if I take my du derivative, I get rid of this regulator, and then I just get this result. Right. Mm-hmm. Right. Mm-hmm. Yeah, so it depends if does it involve a delta function in this? No, it doesn't. Okay, but then probably it's related to this magnetic branch, yeah, which is probably related to some soft modes, or? Exactly, so exactly. Okay, and yeah. Okay, if you want to split the two pieces, okay, that's interesting. Yeah. So let me also say that we matched this two-point function with the standard results in the celestial CFT. So everything is consistent, except that from the point of view of the 2D CFT, you get this delta function, which is a bit exotic from the point of view of a 2D CFT. So we also computed the three-point function, which is the next non-trivial result. And the problem is that the three-point function generically vanishes in Lorentzian signature, which means that you have to go into 2-2 signature. So it's just an analytic continuation that you can do. In that case, the three-point function is non-trivial. So it's given explicitly here. And again, this three-point function will be completely determined up to these choices of branch by the word identities. So we computed explicitly the Fourier transform on this three-point function and checked that this is indeed consistent with what is expected from the world identities. Yeah. Right, so what you get instead of S2 times R for the topology of Scry, you get a celestial torus, which is Lorentzian. So it's a Lorentzian torus times R, the retarded time. That's the only difference. So, yeah. Oh, if you take the Lorentzian signature well, the Euclidean signature for the degenerate metric, you can show that they generically vanish, except in the collinear case. So you have to change the signature at the boundary. If you do the analysis of the world identities for the Carrollian CFT, for the 3-point function, you can show that if you choose the Euclidean metric for the degenerate metric, then the 3-point function generically vanishes. Okay, for the electric. No, probably the magnetic branch will be the one of a 2D CFT, yeah, which is time independent. So yeah, right. Maybe let me just say that in this continuation now, Z and Z bar are treated as real variables, but independent. So that's the difference compared to the Lorentzian signature. So we also computed the 4-point function. This works essentially in the same way. So you just take 4 Fourier transform of the 4-point function in momentum space, and again you can match with the results in celestial holography. But maybe let me jump directly to this endpoint MHV amplitudes. So here I'm presenting the MHV gluon amplitudes, but you have a similar formula for the gravitons. And these are called the Park-Taylor formula. So these are very beautiful and simple formula for these kind of amplitudes. So MHV just means that you have 2 minus and the rest of plus for the helicity. And basically using this decomposition of the momentum conserving delta function in the bulk, you can compute explicitly the Fourier transform. Okay? And once you do that, you get this very compact expression for the Carrollian amplitudes associated with these endpoint MHV 3-level amplitudes. And you can see that this expression, everything boils down in computing this remaining integral, which is this IN here. And in practice, you can compute it case by case. But there is a specific kinematic regime where you can actually get a closed form for this Carrollian amplitude. So you can compute it for any n in that context, and is given by the following expression. So IN is just given by this product, which is provided here. Yes. So, yeah. Mm-hmm. Yes. So we took basically here descendant with respect to U1 ... UN. Yeah. Yes. So that's why there is this tilde there. So let me say that these endpoint correlation function gives some non-trivial dynamical constraints on this putative dual Carrollian CFT. Let me also say that here I presented the result for gluon amplitudes, but you have a similar result for graviton amplitudes. And the amplitude essentially take a very similar form. And in particular, it boils on exactly in computing the same integral at the end. So it can be computed explicitly as well. And let me also emphasize that these Carrollian amplitudes look much simpler than their celestial counterparts, because there you have some hypergeometric function which have some integral representation that you cannot compute explicitly. So it seems that the Carrollian representation is somehow simpler in that case. But what you can show is that, again, using the correspondence between Carrollian and celestial amplitudes, you can recover these hypergeometric function consistently starting from this result for the endpoint Carrollian amplitudes. So we also looked at the collinear limit for the amplitude. So this is a statement of what is happening when you take two external legs to be collinear in a scattering amplitude. And what you can show is that there is a kind of universal factorization that appears, so a split function here, which involves a three-point function. And what you can do is to perform a Fourier transform over this relation here expressed in momentum space. And this allows you to get a definition of what we call a Carrollian OPE block. So remember that here I'm working explicitly in split signature. So I can take Z1 going to Z2, and I keep Z bar and U arbitrary. So that's defined a notion of Carrollian OPE block. And this is basically given by this OPE of the two Carrollian operators at scry, which can be expressed as an infinite sum over some Carrollian descendants. So we follow here the same logic that was taken in the context of celestial holography. Let me mention that this complicated expression for the Carrollian OPE is actually consistent with the Carrollian symmetries. So that's something that we checked explicitly. And I think this was non-trivial because we know that this ultra-local structure for the Carrollian CFT can be a bit tricky. So it's important to check that all the relations that you are writing are compatible with that. And checking that this is invariant under the action of the symmetries is kind of convincing. And what we also did is to match these Carrollian OPE at scry with the expression of the celestial OPE, which are given here and which were obtained before on the celestial sphere, again by starting with the collinear limit, but taking the Mellin transform instead of the Fourier transform. Not always. Sometimes you have to take derivative. Actually, that's something that I will use later when looking at the action of the W infinity symmetries. That will be useful. So there is the same problem that than the two-point function. You can get some divergences, but you can get rid of these divergences by just taking the U derivative. That's actually what I will be doing here. Yeah, so let me mention that there are these W1 plus infinity symmetries that have been found in the context of celestial amplitudes by looking at the algebra that was constructed out of the OPE obtained in the celestial CFT. And this W1 plus infinity symmetry can be traced back to the Penrose nonlinear graviton construction, okay, for self-dual spacetimes. And so the question that we ask here is, what is the action of these W1 plus infinity symmetries that have been found in the celestial framework at scry, okay? So acting on Carrollian operators. And the nice thing is that they can be deduced from these OPE formula very explicitly. So basically the idea is to take one of the operator here and smear it along a generator of scry to define what we call a soft operator. So that's what I'm doing here. I'm defining this generator of W1 to infinity algebra. And so this is a light ray transform that Adrien was mentioning. And these generators here satisfy the W1 plus infinity algebra. So they satisfy these commutation relation here. And so what you can do is to implement this integral transform on one of the insertion here in the Carrollian OPE. And what you get is the following transformation. Notice that I took a derivative with respect to U2 on the second insertion in the OPE to get rid of the divergence. But this is what I get. So this is the action of the W1 plus infinity symmetries on Carrollian graviton operators. So this is how these symmetries are acting at scry. So let me make a comment is that for Q sufficiently small, these actually are local expressions. But if Q becomes bigger than 5/2, then you get some inverse power of du derivative here, which means that the action of W1 plus infinity symmetries at scry is non-local. It's local for the leading, subleading, and sub-subleading soft graviton theorem, but then it becomes non-local. So we also checked that these action on the Carrollian operators was consistent with the action on the celestial CFT operators that was found before in the literature, so everything is consistent. And this is also consistent with the transformation that were found in position space using radiative phase space arguments, so using this H-Strobel Poisson bracket. And this was nicely reviewed by Mark in his talk. So finally, one slide about twistors. So basically, this action of W1 to infinity is very complicated from the scry perspective because it's non-local. And the question is there a better framework to study these symmetries? And it seems that twistor space is a kind of natural framework to study these symmetries because they are acting locally on the space and they correspond to some Poisson diffeomorphism. So they have a very nice geometric interpretation. And so what I'm going to do here is just to relate the Carrollian operator that I've discussed before with some functions on twistor space. So the massless fields in Minkowski space satisfy some equations of motion, and they can be expressed in spinorial languages in the following form. So these are called zero rest massless field equation. And you have two integral representations for these bulk fields. So these are spinor bulk field. The first is the so-called Kirchhoff-Dademar formula that allows you to express a solution of this field equation in terms of the boundary value of the bulk field. So this is the Carrollian operator that I was defining before. And if you want, this is a bit a holographic construction in the sense that you are starting from the boundary value of the field and you are reconstructing the bulk field just using this integral transform. But there is another very useful integral transform that can be considered in that context to express the solution of these equations, which is called the Penrose transform. So this allows you to express solutions of this equation in terms of homogeneous functions defined on twistor space. So f is really a function defined on twistor space, and here, since I'm working in 2-2 signature, my twistor space will be the projective space in 3 dimensions. And basically, you have two integral transforms to express exactly the same field in the bulk. So it means that, in principle, you are free to relate what is happening at the level of the integrants. Can you relate the Carrollian primary with the homogeneous function on twistor space? And the answer is yes, and this is an explicit formula doing that for you. So here in the right-hand side, you have this twistor space function, and in the left-hand side, you have the Carrollian primary. And in particular, you can take the examples of gravity, where the shear can be related explicitly in terms of these homogeneous function. So this kind of map could be useful, especially if you are interested by twistor space amplitudes. And you can map them now directly in terms of Carrollian amplitudes. That's something that you are free to do using these kind of maps. And this could also be useful to understand better why you have these W1 plus infinity symmetries at scry. And in particular, is there some kind of natural geometric structure at scry that will allow to explain why you have these non-local transformation for W1 plus infinity. Okay, so let me just conclude with some summary and perspective. So here I've tried to argue that there were two approaches towards flat space holography, this Carrollian and this celestial proposals, and I've tried to argue that they were actually related and equivalent when applied in the same setup, which means that you are free to choose either of these approaches. I've tried to argue that the Carrollian approach was useful, especially if you were interested by the relation with the ESI CFT correspondence through the flat limit. There should be a C here. And yeah, so we saw that this flat limit in the bulk, implying the Carrollian limit at the boundary, is actually successful in the context of 3D gravity. This also allows to encode consistently the S matrix in terms of boundary Carrollian CFT correlators. And the extrapolate dictionary takes a very natural form in that context because you can just push the bulk correlators at the boundary and get these Carrollian amplitudes. Something that I find kind of exciting is that everything that you can deduce in this Carrollian holography approach could be useful in other fields of research. So for example, Carrollian physics has applications in black holes, cosmology, condensed matter, and fluid, for example. So everything we can learn about this putative Carrollian CFT might be useful in that context. And finally, let me mention some perspective for the following. So the question in which I'm interested now is the relation with the ADS amplitudes. So basically, the amplitudes in ADS are expressed in terms of these ADS return diagrams, and they correspond to some correlators in position space in the boundary CFT. And so the natural object that you expect to have in the flat limit of ADS are precisely these Carrollian amplitudes that I've mentioned here. And so the question is, can we relate explicitly these kind of objects? And finally, here in this talk, I was focusing on a bottom-up approach to flat space holography. But of course, it will be very interesting to try to consider some top-down model for Carrollian holography using this explicit C going to 0 limit. Okay, that's all I wanted to say. Well, thank you very much.